Hello everyone and welcome to this video on using de Moivre's theorem to solve equations. I have to read these, I can't remember them. My name's Darren from Maths Guru. Thank you very much for joining me. Hopefully this video is going to be useful. It is the last video in this particular series on complex numbers for the specialist maths course, but it's useful all over the world. So hopefully you're going to find it useful. Now behind me it just says pretty much what we're going to do. Understand how to use de Moivre's theorem to solve equation, and this really does build on what complex numbers is, how to find lengths, divide, all of that stuff. Now if you want to find where that is, it is on mathsguru.com, totally free to sign up, and pretty much the whole course is going to be on there very shortly, and hopefully it's going to be useful to you. Right, let's go back. Now de Moivre's theorem we have met before in our previous video. The idea that we can express a z, a complex number, in the form of r cis theta, all right, where theta is our argument, and again, all that type of language is really important. If we have z to the m, then basically that is r cis theta, all to the power of n, and using some pretty funky maths that we again in the previous video, we know that we can express that in this form, that basically z to the power of n is r to the power of n cis n theta. Now that makes life a lot easier. But we need to realize that actually this would just be one solution. There are multiple solutions, and as such, it probably makes more sense to think that, you know, z to the power of n, a complex number to a power, can be expressed as r to the power of n. That is the radius from the center. Cis n theta, that would be our initial argument or our initial solution, plus 2 pi theta. Now, again, how that's used is pretty funky. So, for example, let's look at this here. And I have to say, one of the biggest things that I think VCAA like to do is that trip people up and realize that a lot of people don't know that you can actually write a whole number in a different way, particularly in complex form. And so you would have z cubed is equal to 1 cis 0. Wow. Now, as soon as that happens, life becomes a little bit easier. Sorry about my very dodgy 3. All right, why does that make life easier? Because we like to equate with maths. What's on the left is equal to what's on the right. At the moment, z cubed we can actually write now as r cubed cis 3 theta is equal to 1 cis of 0 plus 2k pi. Now that takes into account all of those repeated solutions. Why do we like this? Well, we now know that r cubed is equal to 1. So that means r is equal to 1. We now know that the solutions to this will all lie on the unit circle. Yay! And we now know that 3 theta is equal to try that one again, is equal to 0 plus 2k pi. Or my solutions are 2k pi on 3. What? Exactly. Now we can choose k values in our natural numbers, in our integers, whatever we like, okay? But the point of it is, that is now a way to say that all of our solutions are going to fit on our circle radius 1, yes, and every 2k pi. So when I put k equals 0 in, I get theta equals 0. That means it's going to lie as, you know, a real solution. It's going to be just 1. Then I'm going to have k equals 1. I'm going to have 2 pi on 3 as a solution, and then k equals 2. I'm going to get theta is equal to 4 pi 3, and if I put k equals 3 in, then ultimately I'm going to end up with theta is equal to 2 pi, back to where we start. What? So now there are 3 solutions to all of this. Why is this really helpful to us? Well, I'm going to turn around and say that VCAA generally will give you a beautiful, you know, polar coordinates graph, much like this one here, to be able to plot your information on. Now, my one really sucks because I had to download this one from the interweb, and so it's not very useful. But what I'm going to say is always look for these divisions here, for what they are giving you, because it's a huge hint on what you can use them for. So obviously we got 5 pi on 6 here, 2 pi on 3, pi on 2, pi on 3. But the thing of it is, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 divisions there. So each of those divisions are pi on 12s. Ah, that makes life very useful. Now, if I was going to plot my solutions on here, all right, the first thing is I've got a radius of 1. All right, so they're all going to be on my unit circle. And my first solution is going to have an argument of 0.